Look up at the night sky. Each of those pinpricks of light is a star, a sun, possibly with its own family of worlds. With our most powerful telescopes, we can see even further to other galaxies, swirling collections of billions of stars, stretching off into the seeming endless black. It feels infinite, doesn't it? As if the universe just goes on forever. But here is one of the most profound and unsettling truths of modern cosmology. It is not. What we can see, this grand cosmic panorama, has an edge. There is a limit, a final frontier to our vision, a place beyond which even our most advanced instruments cannot peer. This boundary is known as the cosmic horizon, and the question of what lies beyond it is one of the greatest mysteries in all of science. It is a question that doesn't just challenge our technology, it challenges the very foundations of our understanding of space, time, and reality itself. We are about to embark on a journey to this ultimate edge, to explore the nature of this limit and to confront the astonishing possibilities that might exist on the other side. This journey begins with a simple yet deeply human impulse, the desire to see what's over the next hill. For millennia, that instinct has driven exploration across our planet and then beyond it into the solar system. But the cosmic horizon presents a different kind of challenge altogether. It is not a physical wall you can sail around or a mountain you can climb. It is a wall built by the fundamental laws of physics, by the finite speed of light and the relentless expansion of the universe itself. Light from galaxies too far away has simply not had enough time in the entire history of the cosmos to reach our telescopes. We are, in a very real sense, trapped inside a bubble of observable reality, and we have no way of knowing just how much larger the full universe beyond that bubble might be. Is it just a little bigger? Is it unimaginably vast? Or could it be infinite? This is the enigma of the ultimate cosmic limit. It forces us to ask not just what is out there, but what is the true nature of the cosmos we call home. The answers we are beginning to uncover are more bizarre than any science fiction. They suggest that the universe beyond our horizon could be a chaotic, alien landscape, utterly different from our own, governed by different laws of physics. Or it might contain countless other observable universes, just like our own, islands of reality in an endless cosmic ocean. This isn't just about distant galaxies, it's about the fundamental architecture of existence. In this video, we will trace the path to this horizon, understand why it exists, and grapple with the mind-bending theories that physicists have proposed to explain what lies in the ultimate beyond. This is a frontier that defines not only the limits of our vision, but the limits of human knowledge. To grasp this idea of a cosmic horizon, we first need to understand the stage upon which this entire drama plays out, the observable universe. This is not the entire universe, whatever that may be. Instead, it's our own personal cosmic backyard, the portion of everything that exists from which light has had enough time to travel to us here on Earth. Think of it like being in the center of a vast, dark forest during a foggy night. You can only see the trees that are close enough for the light from your lantern to reach and reflect back to you. The rest of the forest, no matter how immense, remains hidden in the darkness. Our most powerful telescopes are that lantern, and the observable universe is the collection of trees we can see. The key to this entire concept is the fact that light, while astonishingly fast, has a finite speed. It travels at about 1,080,000,000 kilometers per hour. That seems instantaneous to us in our daily lives, but across the cosmic abyss, it creates a profound delay. When you look at the moon, you are not seeing it as it is now, but as it was 1.3 seconds ago. You see the sun as it was 8 minutes in the past, and when we point our telescopes at the Andromeda galaxy, we are witnessing light that left its stars 2.5 million years ago, when early humans were first walking the Earth. We are, in effect, cosmic historians looking back in time with every glance at the sky. Now, take this idea to its ultimate conclusion. The universe is estimated to be 13.8 billion years old. This means that the absolute farthest we could possibly see is the distance that light has been able to travel in that entire time. You might logically think that the observable universe should therefore have a radius of 13.8 billion light-years, giving it a diameter of 27.6 billion light-years. But here's where things get truly fascinating, and where the true nature of the cosmos reveals its strangeness. The actual diameter of our observable universe is calculated to be about 93 billion light-years. That is vastly larger than the simple calculation would suggest. How can this be? The answer lies in one of the most important discoveries in all of science, the expansion of the universe. Space itself is not static, it is stretching. The galaxies are not just flying away from each other through space, the very fabric between them is growing. This means that the light from the most distant objects we can detect has been on an epic journey. It began its travel 13.8 billion years ago from a point that was much closer to us. But as the light moved through space, the space behind it and in front of it was expanding, stretching the wavelength of the light and dramatically increasing the total distance it had to cover to finally reach our eyes. The source of that light is now far more distant than 13.8 billion light-years away, because the universe has been stretching throughout the light's entire journey. So, what is at the very edge of this 93 billion light-year wide sphere? The oldest light we can detect, the cosmic microwave background. This is not the light from the first stars or galaxies. It is the afterglow of the Big Bang itself, a faint whisper of radiation that fills all of space. This background is a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for atoms to form and for the once opaque cosmic fog to clear, allowing light to travel freely for the first time. This glow is our ultimate horizon. It is the final, fundamental barrier to our vision. We cannot see beyond it, not because our telescopes are not good enough, but because the universe before that moment was essentially a wall of hot, dense plasma that was completely opaque. The cosmic microwave background is the final message from the dawn of time, and it marks the boundary of our observable universe. This cosmic horizon, defined by the ancient light of the Big Bang, presents us with a profound and inescapable truth. The barrier is not merely a consequence of time and expansion, but is enforced by the most fundamental rule of the cosmos, the ultimate speed limit, the speed of light. This constant, approximately 299 million meters per second, is not just the speed at which light travels. It is the maximum speed at which any information, any signal, any influence of any kind can move through the fabric of space-time. It is the universe's absolute enforcement of causality, the rule that nothing can overtake a beam of light, and it is this very law that constructs our cosmic prison. Consider what this means for exploration. Our most ambitious visions of traveling to the stars are shackled by this limit. Even if we could build a spacecraft that traveled at 99% the speed of light, a journey to the nearest star system, Alpha Centauri, would still take over 4 years from the perspective of people on Earth. But to reach the edge of our own observable universe, that journey would be fundamentally impossible. Any galaxy near that horizon is not just far away in space, it is receding from us due to the expansion of the universe at a velocity that exceeds the speed of light. This is not a violation of Einstein's laws, because the galaxies themselves are not moving through space faster than light. The space between us is expanding, carrying them away. The result, however, is the same. We could never catch up. No signal we send could ever reach them, and no signal from them sent today could ever reach us. We are forever isolated from those regions. This creates a chilling implication for the future of cosmic discovery. As the universe continues to expand at an accelerating rate, our observable universe is actually shrinking. Distant galaxies are being pushed beyond our horizon, their light becoming too redshifted and faint to ever detect again. Billions of years from now, any civilization in our Milky Way will look up into a much darker sky. All other galaxies will have vanished from view, their light forever lost beyond the cosmic horizon. The universe will appear as an island of stars in an infinite, empty blackness, with no evidence of the grand cosmic community we know exists today. We are living in a uniquely privileged era, a cosmic golden hour when the afterglow of creation is still visible and the scale of the cosmos is still apparent. The speed of light, therefore, doesn't just limit our view, it limits our very connection to the cosmos. It means that a vast portion of the universe is causally disconnected from us. Events happening beyond our horizon can have no effect on us, and we can have no effect on them. They are, for all practical purposes, not part of our reality. This leads to a staggering thought. If the full universe is much larger than what we can see, and all evidence suggests it is, then there are realms of existence, perhaps containing galaxies, stars, planets, and even life, that are forever separated from us by an unbridgeable gulf. We are residents of a cosmic bubble, a pocket of reality defined by the finite journey of light, forever wondering about the nature of the immense and possibly infinite universe that lies eternally beyond our grasp. This expansion, this relentless stretching of the cosmos, is the engine that truly complicates our understanding of the cosmic limit. It transforms a simple barrier of time into a dynamic and ultimately insurmountable wall. The story of this discovery begins not with complex mathematics, but with patient observation. In the 1920s, an astronomer named Edwin Hubble was meticulously studying the light from distant galaxies. He made a startling correlation. With very few exceptions, the light from these galaxies was shifted toward the red end of the spectrum. This redshift is similar to the Doppler effect you hear when an ambulance siren passes you. The sound waves are stretched as the source moves away, lowering the pitch. In the case of light, stretching the waves makes them redder. Hubble's monumental discovery was that the degree of this redshift was directly proportional to the galaxy's distance from us. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, presented an inescapable conclusion. The universe is not static, it is expanding. Space itself is growing, carrying the galaxies along with it like raisins in a rising loaf of bread. As the dough expands, every raisin sees all the other raisins moving away, and the ones farther away recede faster. This leads to a concept that seems to defy common sense: superluminal recession. As we look at galaxies that are extremely far away, the cumulative expansion of the space between us and them means they are receding at velocities that exceed the speed of light. It is crucial to understand this is not a violation of Einstein's theory of relativity. Nothing is moving through space faster than light. Instead, it is the fabric of space itself that is stretching, and there is no known limit to how fast space can expand. The galaxy is, in a sense, stationary within its local patch of space, but the river of space it's sitting on is flowing away from us at an ever-increasing rate. This expansion fundamentally reshapes our cosmic horizon. The edge of our observable universe is not a static shell. It is a moving boundary defined by the point where the recession velocity due to cosmic expansion exactly equals the speed of light. Think of it as a race between light speeding toward us and the space between us stretching, carrying the source of that light away. At the horizon, these two effects are in a perfect, tragic balance. The light from a galaxy exactly at that point is making no net progress toward us. It is running on a cosmic treadmill, its incredible speed matched by the stretching of space. For galaxies beyond that horizon, the expansion wins. Their light, even light emitted at the beginning of time, is being swept away from us faster than it can approach. That light will never, ever reach us. So if the expansion of space is constantly pushing galaxies away, and some are already receding faster than light. What does that mean for the future of what we can see? This brings us to a crucial and often misunderstood concept, the Hubble volume. It's easy to think of the observable universe as a single, fixed bubble, but in reality, there are two different bubbles to consider, and they are changing at different rates. The first is the one we've been discussing, the sphere containing everything whose light has reached us since the Big Bang. But the Hubble volume describes a different, more dynamic frontier. It's the region of space from which light can still reach us eventually. Right now, these two spheres are almost the same size, but they are on a dramatic collision course with the laws of physics themselves. To understand the Hubble volume, imagine you are standing on a shore and the ocean represents the fabric of space. A ship far out at sea sends a message using a flare gun. The flare represents a photon of light. Now, suppose the ocean itself begins to expand, like water being added everywhere at once, creating currents that carry the ship away from you. If the ship is close enough, the flare will still reach you, even as the ocean stretches. The ship is within your Hubble volume. But if the ship is too far away, the expansion of the ocean will carry it back so quickly that the flare, no matter how bright, will make no progress and will never land on your shore. That distant ship has passed beyond your cosmic horizon. In our universe, the boundary of the Hubble volume is defined by a simple but profound balance. It is the distance where the expansion velocity of space is exactly equal to the speed of light. Within this volume, space is expanding, but not so quickly that light cannot overcome the recession and travel towards us. These photons are fighting a headwind, but they are making forward progress. They are the messages from galaxies that, while they are moving away from us, are still connected to our future. We will see their light, but it will be highly redshifted and will arrive far, far in the future. This is the universe that is still causally connected to us. Now contrast this with our current observable universe. That sphere contains all the light that has already had time to arrive. It includes galaxies that are now far beyond the Hubble volume. Their light from the ancient past is just now reaching us, but any new light they emit today is destined to forever travel through an expanding void, never to complete its journey. They are already gone from our future. The most distant galaxy we can see is a ghost. We are observing its portrait from a time when it was still part of our connected cosmos, but its present-day self is forever isolated. This is where the acceleration of the universe's expansion becomes the true villain of our cosmic story. For much of cosmic history, scientists thought the expansion was gradually slowing down due to the mutual gravitational pull of all the matter in the universe. If that were true, the Hubble volume would always be growing, steadily bringing new regions of space into view. Our cosmic future would be one of ever-increasing discovery. But observations in the late 1990s revealed the opposite. The expansion is speeding up, driven by a mysterious force we call dark energy. This changes everything. Because of this acceleration, the Hubble volume is not expanding indefinitely. In fact, it is approaching a fixed maximum size. It is settling into a steady state, while the actual universe beyond it continues to stretch at an ever-increasing rate. This creates a fundamental, unreachable boundary, an ultimate limit. Galaxies that are currently within our Hubble volume are safe for now, but galaxies that are just beyond it are crossing a point of no return. They are being swept over a cosmic waterfall. As space between us and them stretches faster and faster, they will fade from view, their light redshifted into undetectable wavelengths, and then they will vanish entirely from our future causal reality. The truly sobering realization is that most of the universe we see today is already on that list of the lost. The light from the cosmic microwave background, our deepest view into the past, comes from a region that is now about 46 billion light-years away. But due to acceleration, that region is now receding from us at more than 3 times the speed of light. We are receiving its ancient message, but any event happening there now is completely and forever inaccessible. We are archaeologists studying a civilization that has already vanished, its modern inhabitants living in a reality we can never know. This leads to the ultimate chilling conclusion. The accelerating expansion driven by dark energy doesn't just mean that distant galaxies are moving away. It means that the cosmos is actively dismantling our ability to observe it. The universe is gradually isolating every galactic cluster, every island of stars. In the far future, the Hubble volume, the sphere of space that can ever influence us, will contain little more than our own local group of galaxies bound together by gravity. The rest of the universe will have receded into an impenetrable blackness, leaving behind no evidence that it ever existed. The ultimate cosmic limit, then, is not a distant barrier we might one day cross. It is a shrinking cage, a horizon of knowledge that is slowly closing in on us, defining a future where the cosmos becomes a much smaller and lonelier place. So if our cosmic horizon is like the edge of the light from a single campfire in an immense dark forest, a question of staggering proportions emerges. Just how big is that forest? Is our observable universe a tiny sample of a much larger, but still finite cosmos, or is it an infinitesimally small speck within a truly infinite reality? This is not just a philosophical pondering. It is a question that modern cosmology is uniquely equipped to tackle, and the answer hinges on the fundamental geometry of space itself. Scientists have a powerful tool for investigating this grand architecture, the cosmic microwave background. This ancient light, the afterglow of the Big Bang, is not perfectly uniform. It contains tiny, faint variations in temperature ripples that are essentially frozen sound waves from the universe's fiery infancy. By analyzing the patterns and sizes of these ripples with incredible precision, missions like the Planck satellite can essentially measure the overall curvature of the universe. Think of it like this: if you were a tiny ant on a vast surface, you could determine if you were on a flat plane, a sphere, or a saddle shape by measuring the angles of triangles or watching how parallel lines behave. The Planck satellite did this on a cosmic scale. The results were definitive and for many mind-bending. The data indicates that the universe is flat or very nearly so, to an astonishing degree of accuracy. This finding of flatness carries immense implications. In the language of cosmology, a flat universe doesn't mean like a sheet of paper. It means that on the largest scales, the rules of Euclidean geometry we learned in school hold true. Parallel lines never meet or diverge, and the angles of a triangle always add up to exactly 180 degrees. But more importantly, a geometrically flat universe, according to our best models of cosmic inflation, is most simply explained by an infinite extent. To grasp why flatness suggests infinity, consider a simpler analogy: the surface of the Earth. Our planet's surface is positively curved or closed. If you start walking in a straight line, you will eventually return to your starting point. It is finite but unbounded. Now imagine a flat, infinite plane. You could walk forever in any direction and never loop back or hit an edge. The cosmological data points toward our three-dimensional universe behaving like this infinite plane. It could just keep going with no boundary and no end. An infinite universe beyond our observable horizon is a concept that stretches the human mind to its breaking point. It means that every single possibility, no matter how improbable, is not just possible but inevitable. In an infinite cosmos, there isn't just one observable bubble like ours, there are an infinite number of them. Every configuration of matter that the laws of physics allow will occur not just once but an infinite number of times. This leads to some truly staggering consequences. Somewhere far beyond our horizon, there could be an exact duplicate of our Milky Way galaxy, with an exact duplicate of our solar system, and an exact duplicate of you watching a video just like this one. In fact, in an infinite universe, there would be an infinite number of these duplicates, each with infinitesimally small variations. This idea, sometimes called the cosmological multiverse, suggests that the entire history of our cosmic bubble, from the Big Bang to this very moment, is just one story being told in a library that contains every story that can ever be written. It redefines our place in the cosmos. We are not just a small part of a large universe. We are a single, unique pattern in an infinite tapestry of existence, where every possible pattern is woven somewhere in its endless threads. However, we must tread carefully. The conclusion that the universe is infinite is a powerful inference from the data, not a direct observation. Our measurements show the universe is extremely flat, but they cannot rule out a curvature so subtle that the universe is actually shaped like a hypersphere, a four-dimensional analog of a ball, but on such an immense scale that it appears flat to us, just as the Earth feels flat when you stand in a field. In this scenario, the universe would still be finite, but so colossally large that the observable universe is like a single atom on the surface of that cosmic balloon. The true size would be beyond human comprehension, even if it weren't strictly infinite. This distinction between an impossibly vast finite universe and a truly infinite one is perhaps the ultimate cosmic limit we face, a limit not of space, but of our ability to ever know for sure. We are confined to our causal bubble, forever unable to receive information from beyond the horizon. The geometry we measure gives us a powerful clue, but the ultimate nature of the whole remains for now in the realm of theoretical possibility. It is a profound reminder that some of the biggest questions about our existence may have answers that are, by their very nature, permanently hidden from view. But if the universe beyond our horizon is truly infinite, then the most profound implication isn't just more stars and galaxies. It's the possibility that our entire cosmos, with its specific laws of physics and its unique history, might be just one single bubble in a far vaster and more exotic structure, the multiverse. The ultimate cosmic limit, in this view, transforms from a barrier into a shoreline with an ocean of other realities lying just beyond. This idea pushes the notion of a limit to its absolute extreme, suggesting that what we call everything is merely our local neighborhood. The most compelling version of this concept arises directly from our leading theory of the universe's first moments, cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a brief, staggering period of hyper-expansion, ballooning from smaller than a proton to a size larger than our entire observable universe. This solves several major cosmological puzzles, but it also comes with a fascinating consequence. According to the theory, this inflationary process didn't just happen and stop everywhere at once. Instead, it is likely eternal. In some regions, inflation ends, allowing a stable, hot universe like our own to form, a bubble universe. But in the spaces between these bubbles, the inflationary energy field continues to drive exponential expansion. The result is a cosmic foam of bubble universes, each nucleating out of the eternally inflating background. Each of these bubbles could have completely different properties. The fundamental constants of nature, the strength of gravity, the mass of an electron might be set to different values within each one. In some bubbles, the forces might be too weak for atoms to ever form. In others, stars might burn out in an instant. Our universe is simply one where the numbers happen to be just right for galaxies, planets, and life to emerge. In this inflationary multiverse, the ultimate limit of our observation isn't the edge of existence. It's just the boundary of our particular bubble, with an infinite number of other universes, most utterly alien to our own, forever out of reach. Yet another breathtaking possibility emerges not from the vast scales of cosmology, but from the bizarre rules of the infinitesimally small, quantum mechanics. The prevailing Copenhagen interpretation suggests that particles exist in a haze of probability until they are observed, at which point they collapse into a definite state. But the many worlds interpretation proposed by Hugh Everett offers a radically different and more sweeping view. It suggests that every time a quantum event has multiple possible outcomes, all of those outcomes actually occur. The universe doesn't choose one path. It effectively branches into multiple copies, each one realizing a different possibility. In this scenario, every decision you've ever made, every random quantum fluctuation has spawned alternative timelines. There is a universe where you took a different job, a universe where a cosmic ray missed a key strand of DNA and dinosaurs never went extinct, and a universe where every conceivable permutation of history plays out. This isn't a multiverse of separate bubbles in space, but a multiverse of parallel realities constantly splitting off from our own, all equally real. The limit here is not spatial but probabilistic. We are forever confined to a single thread of a boundless tapestry of what could have been. So, are these multiverses science or mere philosophy? Physicists take the idea seriously because it potentially solves a profound mystery. The apparent fine-tuning of our universe, the constants of nature, seem suspiciously perfect for life. If the strength of the dark energy driving cosmic acceleration were even slightly stronger, the universe would have blown apart before galaxies could form. If it were weaker, it would have collapsed back on itself. In a single, unique universe, this perfection seems like an unbelievable coincidence. But in a multiverse, whether the inflationary kind with different constants or the quantum kind with every possibility realized, it becomes inevitable. If there are an infinite number of universes, then it's no surprise we find ourselves in one of the rare ones that can support us. Our existence becomes the selection effect. This redefines the very question of the ultimate cosmic limit. We have moved from asking, what is at the edge of what we can see, to, is our entire reality just one possibility in an infinite ensemble? The horizon we've been exploring may not be the final frontier at all. It could be a temporary curtain, and behind it lies not emptiness, but a collage of creation so vast and varied that the words universe and everything are no longer sufficient to describe it. The search for the limit, it seems, has led us to the threshold of the limitless. We have been journeying outward to the very edge of space that we can possibly observe, but there is another frontier, one that is perhaps even more confounding. It is a limit not of distance but of time. To find it, we must reverse the expansion. We must run the cosmic film backward, pulling all the galaxies, all the matter, all of space itself back together. This thought experiment leads us to an inevitable and startling conclusion. The universe had a beginning. We call this moment the Big Bang, a point of origin some 13.8 billion years ago. And right there, at time zero, we encounter a barrier more absolute than any horizon in space, the initial singularity. A singularity, in the language of physics, is a point where our equations break down, where the quantities we use to describe reality, like density, temperature, and curvature, soar to infinity. The initial singularity of the Big Bang is the ultimate example. It represents a state where the entire cosmos was compressed into a point of zero volume. Imagine taking every single galaxy, every star, every atom in the observable universe, and crushing it into a speck so unimaginably small that it has no size at all. The density and temperature would become infinite. This is not just an extreme condition. It is a place where the very concepts of space and time, as we understand them, cease to have any meaning. This presents the ultimate temporal limit to our knowledge. We can trace the history of the cosmos with remarkable precision back to a tiny fraction of a second after this moment. Our particle accelerators allow us to understand the conditions when the universe was just a seething soup of fundamental particles, and our theories can take us back to the first picosecond, the first nanosecond. But at the moment of the singularity itself, the curtain falls. Our current laws of physics, the twin pillars of general relativity that describes gravity and the large-scale structure of the universe, and quantum mechanics that governs the subatomic world, simply fail. General relativity predicts the singularity with grim certainty, but it cannot describe it. It is as if we have a detailed map of a continent, but the map has a hole burned right through its center, obscuring the most important landmark of all. The problem is one of scale. General relativity is magnificent at describing the warping of space-time by massive objects like stars and black holes. But when all the mass and energy in the universe is crushed into a volume smaller than a single atom, quantum effects must dominate. At these scales, the smooth, continuous fabric of space-time described by Einstein should dissolve into a frothing, chaotic foam, where concepts like before and after may lose all significance. To understand the singularity, we need a theory of quantum gravity, a framework that successfully merges the world of the very large with the world of the very small. Despite decades of effort, we do not yet have a complete and tested theory that can achieve this, so the initial singularity stands as a monument to our current ignorance, a no trespassing sign placed at the dawn of time itself. This leads to a profound question. Did time itself begin with the Big Bang, or was there something before? The idea of a before the Big Bang might not even be a sensible concept if time as we know it was created in that initial event. It is like asking what is north of the North Pole. The question might be based on a flawed assumption. Some cosmological models, like the cyclical universe or the idea of a big bounce from a previous contracting phase, do allow for a pre-Big Bang existence. But for our standard model of cosmology, the initial singularity is the ultimate beginning, the hard edge of time. It is the one moment in all of history for which we have no cause, no explanation, and no physical description. It is the ultimate limit, not just to what we can see, but to what we can ever hope to explain with our current understanding of the laws of nature. But what about a limit in the opposite direction? We have been contemplating the grandest scales of space and time, but what happens if we turn our gaze inward to the very fabric of reality itself? Is there a point where our ability to probe the universe, to divide it into smaller and smaller pieces, simply comes to an end? The answer, according to our most fundamental theories of physics, appears to be a resounding yes. The ultimate limit to smallness is known as the Planck scale, a realm so tiny that it challenges the very meaning of distance and time. To grasp just how small this scale is, consider a simple analogy. An atom is incredibly small. You could line up 10 million of them side by side to equal the width of a single period on this page. The nucleus at the center of that atom is 100,000 times smaller still, but the Planck length is on an entirely different level of miniature. It is about 1.6 times 10 to the negative 35 meters. This means that if you were to magnify an atom to the size of the entire observable universe, the Planck length would be roughly the height of an average tree. It is a dimension so far removed from our everyday experience that it is essentially meaningless in any human context. This isn't just a number pulled from thin air. It emerges naturally when you combine the three fundamental constants of nature: the speed of light, which governs relativity, Planck's constant, which governs the quantum world, and the gravitational constant, which describes the strength of gravity. The Planck length is the scale at which the effects of gravity become as strong as quantum effects. It is the point where our two most successful but incompatible theories, general relativity and quantum mechanics, are forced to confront each other directly, and where both of them break down completely. So, what does it mean for this to be a limit? Think about trying to measure the position of an object. To see something, you need to illuminate it with light. The smaller the object, the higher the energy, or the shorter the wavelength of light you need to use. But here's the catch from quantum mechanics: packing more energy into a smaller volume to probe tinier distances also creates a more powerful gravitational field. As you approach the Planck length, the energy required to make a measurement becomes so concentrated that, according to general relativity, it would collapse into a miniature black hole, instantly swallowing the very phenomenon you are trying to observe. The act of measurement itself destroys the possibility of measurement. It's like trying to use a sledgehammer to probe the delicate structure of a snowflake. You just end up with a puddle. This sets a fundamental, in-principle barrier. The Planck length is the shortest possible distance that can ever have any physical meaning. It is the pixel size of the universe. This leads to a revolutionary idea about the nature of space itself. We tend to think of space as a smooth, continuous backdrop, an empty stage upon which the drama of particles and forces plays out. But at the Planck scale, this smoothness may be an illusion. Instead, space-time might be granular or foamy. Imagine looking at a seemingly smooth piece of fabric through a magnifying glass. You see the tightly woven threads. Look closer with a microscope and you see the individual fibers. The Planck scale is the ultimate microscope for space-time, suggesting that what we perceive as emptiness is actually a seething, chaotic quantum foam. Tiny wormholes might blink in and out of existence, and the very concepts of here and there become fuzzy and undefined. At this scale, the universe isn't a smooth continuum. It's more like the grain of a photograph, and the Planck length is the size of an individual grain. This notion of a fundamental graininess has a profound implication for our earlier discussion of the cosmic horizon and the initial singularity. The Big Bang singularity, where density and temperature become infinite, is a prediction of classical general relativity that ignores quantum effects. But if space-time is granular at the Planck scale, then it cannot be squeezed to a true point of zero volume. There is a smallest possible size. This suggests that the universe did not begin from a singularity, but from an incredibly dense hot state that was still finite. It may have bounced from a previous cosmic cycle or emerged from a quantum fluctuation in some deeper reality. The Planck scale, therefore, doesn't just set a limit to smallness. It may also hold the key to unlocking the mystery of the Big Bang itself, offering a glimpse past the ultimate temporal barrier by revealing that there might not have been a barrier at all, only a transition into a state that our current physics cannot yet describe. Among all the cosmic limits we have explored, from the edge of our observable universe to the dawn of time itself, none is more visceral or absolute than the one created by a black hole. This is not a distant horizon defined by the expansion of space or the finite speed of light. This is a boundary carved directly into the fabric of space-time by pure gravity, a point of no return that stands as a stark monument to the ultimate power of mass and energy. The defining feature of a black hole is its event horizon, a spherical shell surrounding the black hole's core. Think of it not as a physical surface you could touch, but as a one-way membrane in space. Crossing this threshold is the most final act in the universe. Whatever passes through, be it a spacecraft, a planet, or a particle of light, can never come back. It is the ultimate cosmic prison, and its walls are built from the very geometry of reality. The existence of such a place is a direct consequence of Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of spacetime caused by mass. The more mass you compress into a smaller volume, the deeper the gravitational well you create. A black hole forms when an immense amount of mass is crushed into a point of such incredible density that the spacetime around it curves into a closed surface. Within this region, the curvature is so extreme that every possible path that a particle could take, every future that lies ahead, points irretrievably inward toward the center. There are no paths that lead back out. Light, which always follows the shortest path through spacetime, finds itself trapped on a one-way road that only goes deeper into the gravitational abyss. This is why the event horizon gets its name. It is the ultimate horizon of events. Any event that occurs inside is forever hidden from the view of an outside observer. We can receive no information, no light, no signal of any kind from beyond that point. This creates a profound limit not just to observation, but to our very understanding of physics. The event horizon shields us from the black hole's core, a place known as the singularity, According to our equations, the singularity is a point of infinite density and zero volume, where the curvature of spacetime becomes infinite and the known laws of physics simply cease to apply. It is a place where matter as we understand it is crushed out of existence, and the concepts of space and time break down completely. The event horizon acts as a protective barrier, a cosmic censorship that prevents the unpredictable weirdness of the singularity from affecting the outside universe. All we can ever know about a black hole from the outside are its mass, its electric charge, and its rotation. Everything else, all the intricate details about what fell in, is lost forever behind the horizon. This idea is enshrined in the famous phrase, "Black holes have no hair," meaning they are bald, featureless objects, revealing no complexity beyond those three simple properties. The implications of this are staggering. If you were to fall into a stellar mass black hole, the tidal forces, the difference in gravity between your head and your feet, would stretch you into a long, thin stream of atoms in a process whimsically called spaghettification, long before you reach the singularity. But from the perspective of an observer watching you fall from a safe distance, a bizarre relativistic effect would take place. As you approach the event horizon, your image would appear to slow down, becoming redder and dimmer as the light struggles against the immense gravity. To the outside viewer, you would never actually cross the horizon. You would appear to freeze in time, fading from view over an eternity, becoming a permanent, ghostly image etched onto the surface of the black hole. This paradox highlights the clash between general relativity and quantum mechanics. What happens to the information that you represent? Is it truly destroyed at the singularity, violating a fundamental principle of quantum theory, or is it somehow preserved on the event horizon? This black hole information paradox remains one of the most heated debates in theoretical physics, proving that the event horizon is not just a limit to what we can see, but a frontier that challenges our most fundamental ideas about reality itself. This ultimate limit, the event horizon, seems to create a clean and final separation between the universe we can observe and the unknowable interior of the black hole. But in the 1970s, a physicist named Stephen Hawking discovered that this boundary is not as peaceful as it seems. He realized that black holes aren't completely black. They slowly leak radiation and over astronomical timescales can evaporate entirely. This discovery, while revolutionary, ignited a crisis that strikes at the very heart of physics, creating a puzzle so profound it's known as the black hole information paradox. The problem begins with a fundamental principle of quantum mechanics, the conservation of information. In our everyday world, this might not seem important, but at the quantum level, it's a cornerstone of reality. The principle states that information, the specific, unique configuration of every particle, can never be truly destroyed. If you burn a book, the ash and smoke seem like a chaotic mess, but in principle, if you could track every single atom and photon with infinite precision, you could reverse the process and reconstruct the book perfectly. The information about the letters on the page is not gone, it's just fantastically scrambled. This unitarity is a non-negotiable rule for the quantum world. Now consider what happens when something falls into a black hole. According to Einstein's general relativity, all the information about that object, whether it's a dust speck or a library of ancient knowledge, is irretrievably lost behind the event horizon, headed for destruction at the singularity. The universe, from our perspective, has simply deleted that information. This is where Hawking's discovery makes the situation catastrophic. Hawking radiation arises from bizarre quantum effects that occur right at the edge of the event horizon. Empty space isn't truly empty. It's a seething sea of virtual particles, pairs of particles and antiparticles that constantly pop into and out of existence, borrowing energy from the vacuum and annihilating each other so quickly that they don't violate physical laws. But when this happens at the event horizon, a cosmic theft can occur. one particle of the pair might fall into the black hole while the other escapes into space. The escaped particle becomes real, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. From the outside, the black hole appears to be slowly losing mass, glowing like a faint ember. Crucially, however, Hawking's calculations showed that this radiation is completely random and thermal. It contains no information whatsoever about what fell into the black hole. It's like the black hole is emitting pure, featureless heat. So we arrive at the paradox. If a black hole evaporates completely over trillions of years, what happened to all the information about the things that fell in? According to general relativity, it was crushed at the singularity. According to Hawking's original work, it was radiated away as random noise. Both outcomes violate the quantum law that information must be preserved. This creates an irreconcilable conflict between our two most successful theories. Physicists were forced to choose. Either general relativity is wrong about what happens behind the event horizon, or quantum mechanics is wrong about the conservation of information. For decades, this was the uncomfortable stalemate. In an attempt to resolve this, a radical and disturbing idea emerged: the firewall hypothesis. What if the event horizon isn't the smooth, uneventful gateway described by Einstein? What if instead it's a blazing wall of high-energy particles, a literal firewall? The reasoning goes like this. To preserve quantum information, the correlations between the particles falling in and the Hawking radiation coming out must be maintained. But for this to happen, the radiation emitted late in the black hole's life would need to be entangled with radiation emitted much earlier. However, a principle called monogamy of entanglement states that a particle cannot be fully entangled with two different systems at the same time. The particle that fell in long ago is already entangled with its Hawking radiation partner. This creates a problem for an astronaut falling toward the horizon. For the information to be saved, the astronaut must be incinerated by an unimaginably energetic firewall at the horizon itself, breaking the entanglement with the interior and allowing the Hawking radiation to carry the information away. The firewall idea is deeply controversial because it shatters the core principle of general relativity for someone crossing the event horizon, the principle of equivalence. This principle assures us that an astronaut in freefall should feel no dramatic special effects at the moment they cross the horizon. It should be a smooth, uneventful passage. A firewall would mean that the event horizon is not a placid boundary but the most violent place in the universe. This proposal forces a brutal choice: either give up the cherished principles of Einstein's theory, which have been confirmed time and again, or accept that quantum information is truly lost, overthrowing a cornerstone of modern physics. The firewall hypothesis isn't necessarily seen as the final answer, but rather as a stark warning that our understanding of quantum gravity is missing a crucial piece. It highlights that the ultimate limit of a black hole may not be a simple curtain, but a raging inferno where the fundamental laws of the universe are pushed to their breaking point. Yet beyond the dramatic singularities and fiery horizons of black holes lies a limit of a different kind, one that unfolds not with a bang, but with a long, slow, and silent sigh. This is the thermodynamic limit, a final state predicted by the fundamental laws of energy itself. While black holes represent a localized end, the heat death of the universe describes a global and ultimate conclusion for all of cosmic activity. It is a future where the great cosmic engines that power stars, galaxies, and life itself finally sputter and die, leaving behind a cosmos that is not just dark, but fundamentally and eternally still. To understand this profound destiny, we must first grapple with a concept that governs the behavior of energy: entropy. Often described as a measure of disorder, a more precise way to think of entropy is as a measure of the uselessness of energy. Imagine a hot cup of coffee in a cool room. The heat energy in the coffee is highly concentrated and useful. It can do work like warming your hands, but that energy naturally wants to spread out, to dissipate into the cooler room until everything is the same lukewarm temperature. At that point, the energy is still there, but it's so evenly distributed that it can no longer be harnessed to perform any task. The entropy of the system has reached its maximum. The universe is following this exact same path, but on a cosmic scale. The cosmos we see today is a spectacularly low entropy system. We have tremendous imbalances that drive all activity. Stars are colossal fusion reactors, blazing at millions of degrees against the frigid backdrop of space. This temperature difference is what allows work to be done, light to shine, planets to be warmed, and the chemical processes of life to begin. Galaxies collide, converting gravitational energy into light and heat. Every process, from the nuclear furnace at the sun's core to the firing of a neuron in your brain, relies on these pockets of concentrated energy flowing to areas of lower concentration. But with each of these events, a little more useful energy is converted into waste heat, and the overall entropy of the universe increases. It's like a clock slowly winding down. The end game, the heat death, arrives when this winding down is complete. Over timescales so vast they defy comprehension, trillions upon trillions of years, the last stars will exhaust their nuclear fuel. Some will explode as supernova, scattering their enriched guts across space. Others will fade into white dwarfs or collapse into neutron stars and black holes. But these too are temporary reservoirs of energy, over even longer periods through a process known as proton decay predicted by some particle physics theories. The very matter that makes up these stellar corpses could itself disintegrate into subatomic particles and radiation. Even the supermassive black holes, the last bastions of immense gravitational energy, will not last forever. As we just discussed, they slowly evaporate via Hawking radiation, eventually vanishing in a final, faint puff of particles. What remains is a universe that has achieved a state of perfect equilibrium. The temperature will be uniform everywhere, just a fraction of a degree above absolute zero. With no hot spots and no cold spots, no regions of high density or low density, there can be no energy flow. Every process that requires a gradient star formation, chemical reactions, even the movement of atoms will become impossible. The cosmos will be a thin, incredibly dilute soup of fundamental particles and photons, each so far apart from the others that interactions are virtually non-existent. Time will lose its meaning as there will be no events to mark its passage. It will be a changeless, featureless, and eternal darkness. This is the big freeze, the ultimate limit of cosmic evolution, not a dramatic collapse but an endless, silent stagnation. This vision of the far future presents a different kind of limit than the spatial horizons or the singularities we've explored. It is a limit of possibility. The universe will have exhausted its capacity for change, for story, for complexity. It will have played out every possible configuration of its energy and matter and reached a final, static state. The heat death is the ultimate triumph of entropy, the final, quiet victory of dispersion over concentration, signaling an end to all activity and a descent into a permanent, universal stillness. While the heat death presents a slow, cold fade into nothingness, there is another potential end to the cosmos that is far more violent and dramatic. This is the Big Rip, a scenario where the very fabric of reality is torn asunder in a final, catastrophic moment. Both fates are driven by dark energy, the mysterious force causing the universe's expansion to accelerate, but they hinge on a critical and still unknown property of this dark energy, its equation of state, essentially a measure of its staying power. In the heat death, we assume dark energy remains constant, a steady pressure that eventually leads to equilibrium. But what if dark energy is not constant? What if its repulsive force actually grows stronger over time? This possibility leads us to the phantom dark energy model, and the consequences are terrifying. Imagine the expansion of the universe not just as a steady stretching, but as an ever-accelerating runaway train. In this scenario, the repulsive force of dark energy would intensify as the universe grows larger and more diffused. For a long time, the effects would be subtle, even beneficial from a cosmic perspective. The acceleration would help overcome the gravitational pull that binds massive structures together, but gravity is a relatively weak force on these grand scales. The first casualties would be the largest gravitationally bound systems in the universe, galaxy clusters. These immense families of galaxies, held together by their collective gravity, would be pulled apart. The galaxies within them would be flung into the ever-widening emptiness, each set on an isolated trajectory. As the force continues to strengthen, it would set its sights on smaller structures. Next to fall would be individual galaxies like our own Milky Way. The gravitational glue that holds hundreds of billions of stars in a swirling disk would be overcome. Stars would be ripped from their orbits, sent flying off as solitary beacons in an exponentially expanding void. Our solar system, safely nestled within the galaxy for billions of years, would be severed from the whole. But the horror would not stop there. The solar system itself is bound by the sun's gravity. As the dark energy force grows exponentially, it would eventually exceed even this powerful bond. The planets would be torn away from the sun, each becoming a frozen, lonely world on an irreversible journey into darkness. The scale of this destruction would then descend to the truly personal. In the final moments before the Big Rip, the force would become so strong that it would overcome the forces holding individual objects together. The Earth would be ripped apart, mountains, oceans, and continents shattered. Then, the strength holding your own body together, the chemical bonds between molecules, would be vanquished, but the universe would not be done. In the last fleeting instance, the force would exceed the nuclear forces that bind atomic nuclei together, and then even the powerful forces that hold protons and neutrons intact. In a final, unimaginable flash, every atom, every fundamental particle in the universe would be torn apart from every other. Space-time itself, the stage upon which the cosmic drama has played out for billions of years, would be shredded. The universe would cease to be a coherent reality, ending not with a slow freeze, but with a sudden, absolute disintegration. The timing of this potential apocalypse depends entirely on how quickly the phantom dark energy's strength increases. Some models suggest it could happen in as little as 22 billion years from now, a mere blink of an eye on the cosmic calendar. This scenario presents a fundamentally different kind of ultimate limit. It is not a horizon we cannot see beyond, nor a slow fading into silence. The Big Rip is an absolute endpoint in time, a definitive final moment for all structures, all matter, and potentially the very laws of physics as we know them. It is the ultimate expression of a universe whose expansion knows no restraint, a violent conclusion where the force that now gently pushes galaxies apart becomes the engine of total cosmic annihilation. But what if the ultimate limit isn't an end at all? What if it is merely a turning point in an endless cosmic cycle? This is the breathtaking proposition of the cyclic universe model, a concept that directly challenges the finality of both the Big Bang and the Big Freeze. Instead of a single, linear story with a definitive beginning and a cold, silent conclusion, this theory paints a picture of an eternal cosmos, rhythmically breathing in vast expanses of time, with each death giving birth to a new creation. The ultimate limit, in this view, transforms from a wall into a gateway. The foundation of this idea is the Big Crunch, a hypothetical counterpart to the Big Bang. Imagine reversing the expansion we see today. Over trillions of years, if the collective gravitational pull of all the matter in the universe were strong enough to overwhelm the repulsive force of dark energy, the cosmic expansion would gradually slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The background temperature of the universe, now just a few degrees above absolute zero, would start to rise. As everything drew closer, the sky would glow hotter and brighter, eventually becoming an incandescent oven. All structure would be erased as galaxies, stars, and planets are merged and obliterated. The universe would collapse back toward an incredibly hot, dense state, seemingly mirroring the conditions of the Big Bang in reverse. This catastrophic collapse is the Big Crunch, and it appears to be a definitive end. Yet, within this apparent catastrophe, some theories see the seeds of renewal. The concept of the Big Bounce suggests that the universe does not simply vanish into a singularity and cease to exist. Instead, at the moment of maximum compression, when densities and temperatures reach a Planck scale extreme, quantum gravitational effects, those same effects that might prevent a true singularity, could cause the universe to bounce. Rather than collapsing to a point of infinite density, the universe would rebound, triggering a new period of rapid expansion, a new Big Bang. This cycle could, in principle, repeat forever, with each universe containing the ashes of the previous one, reformed into new galaxies, new stars, and potentially new life. The final limit becomes a phase transition, a cosmic rebirth. This elegant idea solves several philosophical puzzles at once. It sidesteps the thorny question of what caused the Big Bang or what existed before it. In a cyclic model, the Big Bang was simply preceded by the contraction of a previous universe. It also offers an alternative to the bleak, eternal emptiness of the heat death. The universe becomes a phoenix, perpetually rising from its own ashes. But for this beautiful theory to be more than just poetry, it must face the harsh light of physical reality, and its greatest challenge comes from the same discovery that pointed toward the Big Freeze, the accelerating expansion driven by dark energy. The observed acceleration of the universe presents a major obstacle for the classic cyclic model. If dark energy continues to push galaxies apart with ever-increasing strength, then the gravitational pull required to eventually halt and reverse the expansion becomes a distant fantasy. The universe appears to be headed for indefinite expansion, not a contraction. For the Big Bounce to be a viable theory, cosmologists must find a way to incorporate dark energy into the cycle. Some speculative models propose that the nature of dark energy could change over time. Perhaps this repulsive force is not constant but is a field that can decay or transform. In this scenario, the acceleration we see today might be a temporary phase. Billions of years from now, dark energy could weaken, allowing gravity to once again dominate and pull the universe back together, setting the stage for the crunch and the subsequent bounce. Another fascinating variation comes from combining cyclic cosmology with string theory in a model known as the ekpyrotic universe. In this scenario, our three-dimensional universe exists as a brane, a shorthand for membrane within a higher dimensional space. The Big Bang could be the result of a collision between our brane and a parallel one. After the collision, the universes bounce apart and expand, eventually slowing down and attracting each other gravitationally again for another collision, creating a new cycle. This model provides a specific mechanism for the bounce that relies on extra dimensions, offering a potential pathway that avoids the singularities where our current laws of physics break down. While the cyclic universe model is a compelling and elegant alternative to a single, finite cosmos, it remains a highly speculative frontier of theoretical physics. We currently lack the observational evidence to confirm that a bounce is possible or that our universe's expansion will ever reverse. The evidence we do have strongly points toward perpetual acceleration. Yet the idea endures because it speaks to a deeper pattern we see throughout nature: the cycle of the seasons, the life and death of stars, the rhythmic beating of a heart. The notion that the cosmos itself might participate in this grand, eternal rhythm is a powerful and humbling thought. It suggests that the ultimate limit we have been searching for may not be a boundary in space or time, but simply the turning of a page in an infinite cosmic story. But how did our observable universe, this 93 billion light-year wide bubble, get to be so large, so uniform, and so flat in the first place? The standard Big Bang theory, for all its success, left cosmologists with some deep and puzzling questions about the initial conditions it required. To solve these puzzles, scientists had to propose an even more dramatic event right at the dawn of time, a period of breathtakingly rapid expansion known as cosmic inflation. This wasn't the steady, gradual expansion we see today, governed by dark energy. This was a hyper-driven, exponential stretching of space itself that occurred in the tiniest fraction of a second after the universe began. Let's consider the problems inflation was designed to solve. The first is the horizon problem. When we look at the cosmic microwave background radiation coming from opposite sides of the sky, we see regions that have the same temperature to an incredible precision, to within 1 part in 100,000. This seems logical until you realize that these two regions are separated by about 90 billion light-years. According to the standard Big Bang model, there hasn't been enough time since the beginning of the universe for light or any kind of influence to travel between them to even out their temperature. It's as if you walked into a vast room and found 2 glasses of water on opposite sides that had settled to exactly the same temperature, even though they had never been in contact. How could they possibly have coordinated this? The universe, in its youth, shouldn't have been so uniform. The second puzzle is the flatness problem. As we discussed, measurements show the universe is geometrically flat. But for the universe to remain flat for 13.8 billion years, its initial density at the Big Bang had to be fine-tuned to an absurdly precise value. Imagine balancing a pencil perfectly on its tip. The slightest deviation would cause it to topple over almost instantly. Similarly, if the universe's density had been even a tiny fraction higher or lower at the start, it would have either recollapsed into a big crunch long ago or expanded so rapidly that no galaxies could ever have formed. The fact that we see a stable, flat universe today suggests the initial conditions were set with unbelievable precision. Inflation offers an elegant solution to both of these mysteries. The theory proposes that around 10 to the power of -36 seconds after the Big Bang, the universe was filled with a peculiar form of energy that created a powerful repulsive gravitational effect. This caused space to expand at an exponential rate, doubling in size every tiny fraction of a second. In less time than it takes for light to cross a proton, a region smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. This incredible burst of growth is what we call inflation. Now, see how this solves the puzzles. Before inflation, the entire region that would become our observable universe was minuscule, a tiny speck where everything was in close contact. This tiny region had plenty of time to reach a uniform temperature, just like a small cup of coffee stirs itself to an even warmth. Then, inflation acted like a cosmic microscope, taking that small, smooth, thermalized patch and stretching it to an immense scale. The entire sky we see today, with its uniform background temperature, was once a single, connected neighborhood. The horizon problem vanishes. Inflation also naturally produces a flat universe. Think of the surface of a balloon. When it's small, you can see its curvature clearly. But if you inflate that balloon to the size of the Earth, its surface would appear perfectly flat to someone standing on it. In the same way, the violent stretching of inflation would have flattened out any initial curvature in the fabric of space-time, inevitably leading to the geometrically flat universe we observe. The incredible fine-tuning is explained not by chance, but by the dynamics of inflation itself. It forcefully drives the universe toward flatness. This leads to the most profound implication of all. The patch of space that was inflated to become our entire observable universe was just a tiny part of a much larger, pre-existing reality. And if that larger reality was also undergoing inflation, which is a key feature of the theory, then it is likely that inflation is eternal. While it ended in our patch to create our Big Bang and the universe we know, it continues unabated in the wider landscape. This means that our entire cosmic history from the first second to today is just one bubble in a frothing sea of inflating space. Other bubbles completely disconnected from ours would have nucleated at different times, each becoming its own universe with potentially different properties. The region of space from which our universe originated is immeasurably larger than what we can see, implying that the full, true cosmos is vaster than we can possibly conceive, likely containing an infinite number of bubble universes just like our own. Inflation doesn't just explain the features of our universe, it suggests that our universe is a single grain of sand on an infinite beach. This grand cosmic story, from the inflationary burst to the possible cycles of birth and rebirth, all hinges on the behavior of the universe's most fundamental components. Yet, when we tally up everything we can see, all the stars, galaxies, and interstellar gas, we are forced to confront a staggering and humbling fact. The familiar matter that makes up our bodies and our world accounts for a mere 5% of the universe's total mass and energy. The remaining 95% is composed of two mysterious entities that we cannot see, cannot touch, and do not fully understand: dark matter and dark energy. It is a profound irony that the ultimate fate of the cosmos is being dictated by forces that are, for now, almost entirely hidden from our view. Our ignorance of their true nature represents perhaps the most significant limit on our ability to predict the final boundaries of reality. Let's first consider dark matter. We know it exists not because we can see it, but because we can observe its powerful gravitational influence on the things we can see. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. He noticed that the individual galaxies were moving around within the cluster at such tremendous speeds that, according to the laws of gravity, the collective mass of all the visible stars and gas should not have been nearly enough to hold the cluster together. The galaxies should have simply flown apart. It was as if you were watching children on a merry-go-round spinning so fast that the centrifugal force should fling them off, yet they remained securely in place. Zwicky concluded that there must be some unseen, massive substance providing the extra gravitational glue. He called this missing mass Dunkel Materie, or dark matter. Since then, evidence for dark matter has become overwhelming. We see its signature in the way galaxies rotate. Stars at the outer edges of spiral galaxies orbit just as fast as those near the center, defying expectations unless the galaxy is embedded in a massive, invisible halo of matter. We see it through gravitational lensing, where the gravity of massive galaxy clusters bends the light from more distant objects, acting like a cosmic magnifying glass. The amount of bending is far greater than the visible mass alone can account for, revealing the presence of a vast, unseen scaffold. This dark matter forms the backbone of the cosmic web, the intricate structure upon which galaxies form and cluster. Without it, the universe as we know it would not exist. Yet, despite knowing it's there, we have no idea what it's made of. It does not interact with light or any part of the electromagnetic spectrum. It neither emits, absorbs, nor reflects any radiation. It only seems to interact through gravity. This makes it incredibly difficult to detect directly, and decades of sophisticated experiments deep underground have yet to definitively catch a single dark matter particle. Our inability to identify the very substance that shapes the large-scale structure of the cosmos is a glaring boundary in our knowledge. If dark matter acts as the cosmic architect, providing the gravitational pull that builds structure, then dark energy is the phantom force that works in opposition. Discovered in the late 1990s by observing distant supernova, dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. This was a shocking revelation. Everyone expected that the gravitational pull of all the matter in the universe would be slowing the expansion down. Instead, we found that the expansion is speeding up, as if some mysterious repulsive force is steadily pushing space itself apart. Think of it like throwing a ball into the air, and instead of it slowing down and falling back to Earth, it shoots away from you faster and faster, defying gravity. Dark energy is that inexplicable push. What makes dark energy even more mysterious is that it appears to be a property of empty space itself. The energy density of the vacuum of space, what we might call the energy of nothing, seems to be non-zero and constant. As the universe expands and new space is created, more of this dark energy appears, leading to a feedback loop that drives the acceleration ever faster. The nature of this energy is one of the biggest enigmas in physics. Is it a cosmological constant, as Einstein once proposed, a fixed and immutable feature of the vacuum? Or is it a dynamic field that could change over time, perhaps weakening or even reversing its effect in the far future? The answer to this single question holds the key to the ultimate fate of everything. This is where our ignorance becomes a direct limit to our cosmic forecasting. The long-term destiny of the universe, whether it faces a heat death, a big rip, or even a future contraction, depends entirely on the precise properties of dark energy. If it remains a constant force, as current evidence tentatively suggests, then the universe will continue on its path toward the cold, dark, and dilute heat death we discussed. But if dark energy intensifies, becoming what physicists call phantom energy, then the Big Rip scenario of total disintegration becomes a terrifying possibility. Conversely, if dark energy were to somehow decay away, gravity could reassert its dominance, potentially leading to a big crunch and a cyclical universe. We are, in effect, trying to predict the final chapter of a story without being able to read the most crucial paragraphs. The fact that these two invisible components constitute 95% of reality, while our understanding of them remains in its infancy, is the most profound testament to the limits of our current cosmic perspective. The ultimate boundaries of the cosmos are not just set by the speed of light or the nature of time. They are being written by forces we have only just begun to detect. So we return to this ancient light, this fossil from the dawn of time that defines the very edge of our vision. The cosmic microwave background is far more than just a historical artifact. It is the ultimate boundary, a tangible screen upon which the earliest moments of the universe are permanently projected. To understand it is to understand the fundamental architecture of our cosmic home. This afterglow dates from a very specific moment in cosmic history, when the universe was just 380,000 years old. Before that time, the cosmos was an inferno of plasma, a dense, searing hot soup of protons, electrons, and light. In such a state, photons of light couldn't travel freely. They would constantly crash into free electrons, scattering in every direction, making the entire universe an opaque, glowing fog. It was a cosmic version of being inside a cloud, where you can only see a short distance in any direction. But as the universe expanded, it cooled. When the temperature dropped to around 3,000 degrees, a pivotal event occurred. Electrons were finally moving slowly enough to be captured by protons, forming the first neutral hydrogen atoms. This event is called recombination, though it was really the first combination. In an instant, the free electrons that had been scattering the light were suddenly bound up inside atoms. The fog lifted. The universe, for the first time, became transparent. The photons that had been bouncing around in that plasma were suddenly set free, and they have been traveling across the expanding universe ever since, their wavelengths stretched by that expansion from visible light into the microwave part of the spectrum. This is the light we detect today as the CMB. It is quite literally the flash from the moment the universe became see-through, and it comes to us from every direction, having traveled for nearly 14 billion years to reach our telescopes. When you see a screen of static on an old analog television, about 1% of that snow is the CMB, the faint whisper of creation itself. But the true power of the CMB isn't just its existence, it's in its exquisite detail. When we map this fossil light with incredible precision using satellites like Planck, we find that it is not perfectly uniform. It is etched with tiny variations in temperature, minuscule differences of about 1 part in 100,000. These are the cosmic seeds from which everything we see today would eventually grow. These fluctuations are not random noise. They are a frozen record of sound waves that were traveling through the early universe. In that primordial plasma, gravity was trying to pull matter together into dense clumps, while the intense radiation pressure was trying to push it apart. This created a tug-of-war, resulting in rhythmic compressions and rarefactions, sound waves racing through the cosmic medium. The size of the largest possible wave that could have traveled in the 380,000 years before recombination left a specific imprint on the CMB, a preferred scale that appears as a peak in the statistical analysis of the temperature map. By measuring the angular size of these fluctuations on the sky, cosmologists can perform a remarkable feat of geometry. It's like a cosmic version of surveying. Imagine you have a ruler of a known length and you hold it up at different distances. The farther away it is, the smaller it appears. The preferred scale imprinted on the CMB is our standard ruler. By measuring how big it looks to us on the celestial sphere, we can determine the overall geometry of the universe through which that light has traveled. If the universe were positively curved like the surface of a sphere, the light rays would converge, making the features appear larger. If it were negatively curved like a saddle, the light rays would diverge, making the features appear smaller. The Planck satellite's measurements showed with stunning accuracy that the features appear exactly the size expected for a flat universe. The light rays have traveled in straight lines. This observation of flatness is one of the strongest pieces of evidence that the universe is either infinite in extent or so colossally large that it appears flat to us, like the surface of the Earth feeling flat when you stand on it. Furthermore, the precise patterns of these hot and cold spots allow scientists to create a detailed inventory of the cosmos. The way the sound waves oscillated is exquisitely sensitive to the contents of the universe. By analyzing the CMB, we can calculate the total amount of matter and energy present. The results are what led us to the shocking composition we know today: about 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB fluctuations tell us how much total matter exists through its gravitational effects on the plasma, and the large-scale patterns reveal the influence of dark energy on how those patterns were projected across the sky. This ancient light is therefore not just a boundary, it is a complete cosmic blueprint. It reveals the shape, size, and ingredients of our entire observable universe, all encoded in a whisper of microwave radiation that has traveled since the very dawn of time. It is the ultimate message in a bottle, and we have learned to read every word. And yet, even this profound boundary, the cosmic microwave background, is not the final wall. It is merely the point where the universe became transparent to light. But what if we could find a way to see past this wall, to listen for echoes from the truly primordial universe, from the first frantic moments of the Big Bang itself? This is not a fantasy, it is the promise of an entirely new form of astronomy, one that doesn't rely on light at all, but on the very fabric of space-time. We are now learning to detect the faint ripples in reality known as gravitational waves, and they offer a window to a time before stars, before atoms, even before the cosmic microwave background was emitted. To understand how this is possible, we need to revisit Einstein's vision of gravity. He taught us that space and time are not a static stage but a dynamic, flexible fabric, a four-dimensional continuum we call space-time. Massive objects like stars and planets warp this fabric, creating what we perceive as gravity. Now, imagine the most violent events in the cosmos, the collision of two black holes, each with the mass of dozens of suns. As these unimaginably dense objects spiral toward each other at a significant fraction of the speed of light, they don't just move through space-time, they churn it. Their immense acceleration sends powerful disturbances racing outward, not as particles or light, but as waves of stretching and squeezing in the fabric of space-time itself. These are gravitational waves. They travel at the speed of light, passing through matter almost completely unimpeded, carrying with them a pure, undistorted story of the cataclysm that created them. The direct detection of these waves in 2015 by the LIGO Observatory was one of the most monumental achievements in scientific history, confirming a century-old prediction and opening a fundamentally new sense with which to perceive the universe. But while detecting waves from black hole mergers is revolutionary, it is the potential to detect a far quieter, far more ancient hum that could truly shatter the ultimate cosmic limit. This is the gravitational wave background, a theoretical sea of ultra-long, wavelength ripples that could have been generated in the first instance after the Big Bang. During the universe's earliest, most energetic phases, the entire cosmos was a maelstrom of fluctuating energy densities. These violent fluctuations would have shaken space-time itself, generating a background cacophony of gravitational waves that would still be reverberating through the universe today, much like the cosmic microwave background is the leftover glow of its hot youth. This is where the potential to peer past the CMB becomes reality. The cosmic microwave background is a wall because the early universe was opaque to light. But it was completely transparent to gravitational waves. Those primordial ripples would have streamed freely through the hot, dense plasma unaffected. They have been traveling for the entire history of the universe, and they hold information from a time that is completely inaccessible to traditional astronomy. If we can learn to detect this fossil gravitational wave background, it would be like having a recording of the universe's birth cries. It could carry an imprint of the universe when it was less than a second old or even younger. The most exciting target for this search is the period of cosmic inflation, that fantastically rapid expansion thought to have occurred a fraction of a second after the beginning. The inflationary process, driven by a colossal repulsive energy, would have been incredibly violent. The quantum fluctuations that were present in the inflationary field, tiny, random jitters at the smallest possible scale, would have been stretched by inflation to astronomical sizes. These quantum jitters are believed to be the seeds for all the large-scale structure in the universe, the galaxies and clusters we see today. But crucially, they would have also produced a unique signature in gravitational waves. The pattern of these primordial gravitational waves would be a direct probe of the energy scale of inflation, telling us what kind of physics drove the universe's incredible growth spurt. Detecting them would be the smoking gun for inflation and would allow us to study physics at energies 1 trillion times higher than what we can achieve in our largest particle accelerators. The search for this signal is already underway, using ingenious methods that don't involve building a larger version of LIGO. The key insight is that a passing gravitational wave very slightly alters the distance between objects. Scientists are using natural cosmic rulers to look for this effect. One method involves studying the cosmic microwave background itself with extreme precision. A background of primordial gravitational waves would have subtly polarized the CMB light in a specific swirling pattern known as a B-mode polarization. Finding this unique fingerprint imprinted on the oldest light we can see would be indirect but powerful evidence of those waves from the dawn of time. Other projects are using arrays of dead stars called pulsars, which spin with the regularity of atomic clocks, sending out incredibly precise radio pulses. By monitoring a network of these pulsars across our galaxy for decades, astronomers are looking for correlated, minuscule changes in their pulse arrival times that would be caused by a gravitational wave background gently stretching and compressing the space between us and them as it passes through. Success in this endeavor would transform our understanding of the ultimate limit. It would allow us to do the seemingly impossible, to observe the universe before it was even a universe as we know it, to gather empirical data about the moment of its creation. This isn't just pushing back a horizon, it's finding a way to receive a signal from the other side of the wall. The quest to detect these primordial ripples is a direct assault on the final frontier of our knowledge, an attempt to listen to the story of space-time itself, a story that began before light could even travel freely. So while gravitational waves offer a way to listen to the dawn of time, they highlight a more immediate and humbling reality for humanity. We are, for now, cosmic prisoners. Our vision extends nearly 14 billion years into the past, but our physical reach is confined to a tiny, minuscule corner of our own solar system. The same laws of physics that allow us to see the edge of the observable universe conspire to make traveling to it fundamentally impossible. The grandeur of the cosmic horizon is matched only by the sheer scale of the void that separates us from it. The first and most brutal hurdle is distance. We often speak in terms of light years, but the true meaning of that unit is difficult to grasp. A light year is the distance light travels in 1 year, which is about 9.5 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is 4.2 light years away. That means that even if we could build a spacecraft traveling at the speed of light, a journey to our next-door neighbor would still take over 4 years. But with our current technology, the picture is far more sobering. The Voyager 1 probe, launched in 1977, is the farthest human-made object from Earth. It travels at about 60,000 kilometers per hour. At that blistering pace, it would take Voyager over 70,000 years to reach Proxima Centauri. These are not engineering challenges, these are chronological chasms that span civilizations. This brings us to the ultimate speed limit, the cosmic speed trap set by Einstein's theory of relativity, the speed of light. It's not merely a suggestion, it's a fundamental rule woven into the fabric of space-time. As an object with mass accelerates closer and closer to the speed of light, its mass effectively increases, requiring exponentially more energy to continue accelerating. To actually reach the speed of light would require an infinite amount of energy, a physical impossibility. This isn't a limitation of our engines or fuel, it's a law of the universe. So, even in our most optimistic dreams of future technology, we are forever capped at some fraction of light speed. And at those high velocities, new challenges emerge, like the danger of interstellar dust. A tiny speck of dust, when colliding with a ship traveling at 90% the speed of light, would carry the explosive energy of a nuclear bomb. Shielding against such a relentless barrage presents an almost insurmountable engineering nightmare. Faced with this, scientists have proposed theoretical workarounds that bend, rather than break, the rules of physics. The most famous is the concept of the wormhole, a hypothetical tunnel through the fabric of space-time that could create a shortcut between two distant points. While mathematically possible within general relativity, there is no evidence that wormholes exist or that they could be stabilized. Theorized to be incredibly unstable, a wormhole would likely collapse the instant anything tried to pass through, unless it was propped open by a form of matter with negative energy density, something we have never observed. Another idea is the Alcubierre warp drive, which proposes not moving through space, but contracting space in front of a ship and expanding it behind, effectively riding a wave of space-time. The ship itself would remain stationary inside a warp bubble, thus avoiding the relativistic problems of high speed. However, this concept also requires exotic matter with negative energy to function, placing it firmly in the realm of speculation for the distant future. If faster-than-light travel remains a fantasy, then the only conceivable way to cross the interstellar gulf is to accept the timescale and think in terms of generations. This is the idea of a generation ship, a self-sufficient ark that would journey for centuries or millennia. The people who arrived at a distant star would be the descendants of those who began the voyage. The challenges here are less about physics and more about biology, sociology, and engineering on an epic scale. How do you maintain a closed ecological system for thousands of years, recycling every ounce of water and nutrient without failure? How do you preserve a stable society free from catastrophic conflict or genetic stagnation over hundreds of generations in the isolating darkness of space? The generation ship is a testament to human ambition, but it underscores the profound sacrifice required, turning the dream of exploration into a multi-generational project with an uncertain payoff. And then we must confront the most disheartening limit of all, one we discussed earlier, the accelerating expansion of the universe. Due to dark energy, any galaxy beyond our local group, the small collection of galaxies gravitationally bound to the Milky Way, is already on a one-way trip out of our reach. Their recession velocity will only increase over time. This means that even if we somehow mastered light speed travel a billion years from now, a vast portion of the cosmos we can see today would already be forever unreachable, swept away by the stretching of space itself. The universe is, in a very real sense, putting its most interesting destinations on a moving walkway headed away from us, and that walkway is speeding up. So, will humanity ever physically reach the cosmic horizons we can see? The answer, based on our current understanding of physics, appears to be a definitive no. The horizon defined by the cosmic microwave background is not a place we can ever travel to. It is a moment in time, a view into the infant universe that is now 46 billion light-years away and receding from us faster than light. We are like sailors on an island, able to see other islands on the distant horizon, but with an ocean between us that is growing wider every second. Our destiny may not lie in conquering the vast emptiness between galaxies, but in understanding it from our small, isolated outpost. The ultimate journey may not be one of physical travel, but of intellectual and technological ingenuity, finding new ways like gravitational wave astronomy, to listen to the cosmos and piece together its grand story without ever leaving our home. But what if the ultimate limit isn't a physical barrier at all, but a question about why the universe is structured in such a way that allows us to be here to ask these questions in the first place? This brings us to one of the most profound and debated ideas at the intersection of cosmology and philosophy, the anthropic principle. It begins with a startling observation about our universe's foundation. The fundamental constants of nature, the precise numerical values that dictate the strength of gravity, the power of the electromagnetic force, and the mass of subatomic particles, appear to be suspiciously fine-tuned for life. If any of these values were altered by even a minuscule amount, the universe as we know it would be impossible. Consider the force of gravity. If it were slightly stronger, the gravitational pull within stars would be more intense, causing them to burn through their nuclear fuel at a dramatically faster rate. A star like our Sun might last only a few million years instead of billions, snuffing out any chance for planets to form and for life to evolve on the timescales we understand. On the other hand, if gravity were a little weaker, it might not have been strong enough to pull matter together to form stars and galaxies in the first place. The cosmos would remain a cold, dark, and featureless haze of hydrogen gas. Similarly, the force that holds atomic nuclei together, the strong nuclear force, is balanced on a razor's edge. If it were just a few percent weaker, protons and neutrons wouldn't stick together and complex atoms could never form. There would be no carbon, no oxygen, no building blocks for planets or people. But if it were slightly stronger, protons could bind together so easily that all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for the long-lived stars that life-bearing planets orbit. It seems as though the universe's dials were set with incredible precision to values that permit our existence. This apparent fine-tuning presents a puzzle. Is it merely a monumental coincidence, or does it point toward a deeper truth about the nature of reality? the anthropic principle offers a way to think about this puzzle. In its simplest form, it states that the observed values of the universe's physical constants must be compatible with the existence of conscious life that can observe them. In other words, we shouldn't be surprised to find ourselves in a universe capable of producing us. It's a selection effect. Imagine a group of intelligent fish marveling at how perfectly their pond is designed for them. The water is exactly the right temperature, it contains just the right amount of oxygen, and the food supply is abundant. They might conclude that the pond was fine-tuned for fish, but of course they live in that specific pond precisely because its conditions allow them to exist. They would not be having the conversation in a pond that was toxic or frozen solid. We are in a similar position. We can only observe a universe that has the right conditions for our evolution. This logical observation, often called the weak anthropic principle, is relatively uncontroversial. It simply cautions us against drawing deep conclusions from a sample size of one. However, the principle has a much stronger version that ventures into far more speculative territory. The strong anthropic principle suggests that the universe must have properties that allow life to develop within it at some stage in its history. This statement carries an air of purpose or design, implying that the laws of physics are somehow compelled to lead to conscious observers. For some, this points toward a creator or a teleological force guiding the cosmos. For others, it finds a compelling explanation not in design, but in the existence of a multiverse. This is where the idea of the ultimate cosmic limit expands into something almost limitless. If our universe is just one of a vast, perhaps infinite, number of universes, each with its own random set of physical constants, then the fine-tuning problem vanishes. In an infinite multiverse, every possible combination of constants will be realized somewhere. There will be universes where gravity is too strong for stars to form, universes where atoms never coalesce, and universes that collapse back on themselves instantly. These are dead universes, devoid of observers, but there will also be a tiny, statistically inevitable fraction of universes where the numbers happen to fall into the narrow Goldilocks zone that permits complexity and life. We, of course, find ourselves in one of those rare, habitable bubbles simply because we couldn't exist anywhere else. Our universe isn't special because it was designed for us. It's special to us because it's the only type of universe we could ever inhabit. The multiverse concept, whether arising from eternal inflation or the many worlds interpretation of quantum mechanics, turns the anthropic principle from a philosophical curiosity into a potential scientific framework. It replaces the need for a single, inexplicably perfect universe with a landscape of possibilities where our existence becomes an inevitable outcome of probability applied to an immense canvas. Yet, this proposed solution also highlights a profound limit to our scientific inquiry. If other universes are permanently beyond our causal horizon, forever disconnected from us by the inflationary expansion of space itself, then the multiverse hypothesis may be fundamentally untestable. We might never gather direct evidence of these other realms, leaving the anthropic principle as a powerful, but potentially unprovable, explanation for the seemingly miraculous fine-tuning we observe. It forces us to confront the possibility that the ultimate reason for our universe's hospitable nature may be a truth that is, by its very definition, hidden from us forever. But what if all these limits, the cosmic horizon, the Planck scale, the speed of light, are not fundamental properties of reality, but merely constraints of the system we are running on? This idea pushes the concept of a boundary to its most radical extreme, the simulation hypothesis. It proposes that our universe, with all its galaxies, stars, and the entire tapestry of our lived experience, is not base reality, but an incredibly sophisticated simulation, akin to a hyper-advanced video game. In this view, the ultimate cosmic limit is not a physical barrier at all, but a computational one, defined by the processing power and memory of whatever or whoever is running the program. The argument for this startling possibility often begins with a simple extrapolation of technological trends. Consider the trajectory of our own computing power. In just a few decades, we have gone from simple, blocky graphics in early arcade games to immersive virtual reality environments that can feel startlingly real. If this progress continues for centuries or millennia, it seems plausible that a future civilization could possess the computational resources to create a simulation so detailed that it includes conscious beings who are completely unaware they are living inside a constructed reality. Now, if such a civilization could run not just one, but a vast number of these simulations, each with its own slightly different history and physical laws, then the number of simulated minds would vastly outnumber the minds in the original base reality. From a statistical standpoint, if you are a conscious being, the odds are overwhelmingly high that you are living in one of the many simulations, rather than in the single, original universe. This probabilistic reasoning, popularized by philosopher Nick Bostrom, suggests that one of three propositions must be true. Either civilizations like ours always go extinct before reaching a post-human stage capable of such simulations, they have no interest in running ancestral simulations, or we are almost certainly living in a simulation ourselves. Supporters of the hypothesis also point to what they see as potential glitches in the matrix, or at least features of our universe that could be interpreted as computational shortcuts. The finite speed of light, for instance, could be seen as a mechanism to limit how much of the simulation needs to be rendered at any given time. Much like a video game only loads the detailed environment immediately around the player. The weird, probabilistic nature of quantum mechanics, where particles exist in a haze of possibilities until observed, has been compared to a computer program that only calculates the definitive properties of an object when it is being looked at, a technique used in modern game design to conserve processing power. Even the discrete, granular nature of reality at the Planck scale could be interpreted as the pixel size of the simulation, the fundamental resolution of the cosmic display. However, this hypothesis is met with powerful counterarguments. Physicists like David Deutsch and Sean Carroll have pointed out that simulating an entire universe down to the quantum level of every single particle would require a computer more massive than the universe itself, which seems logically paradoxical. If you need a computer the size of a universe to simulate a universe, what is simulating the computer? Proponents counter that a simulation wouldn't need to be perfect. It could use approximations and shortcuts for phenomena that are never directly observed, just as a video game doesn't simulate the physics of every single blade of grass in a field. Yet, the more we learn about our universe, the more deeply interconnected and consistent its laws appear to be, from the quantum world to the cosmic scale, which argues against it being a patchwork of approximations. The most profound implications of the simulation hypothesis are not scientific but philosophical. If it were true, it would redefine our understanding of existence, consciousness, and even divinity. The laws of physics would not be fundamental truths discovered through inquiry, but merely the rules of the simulation which could potentially be altered or hacked. The search for a unified theory of everything would be the search for the underlying code of the program. The idea of a creator God could be replaced by the concept of a programmer or team of programmers whose motivations for running our simulation are entirely unknown. Are we a scientific experiment, a form of entertainment, or a historical archive? This line of thinking can lead to existential vertigo, making our struggles, achievements, and the very meaning we ascribe to life feel potentially trivial. Yet it could also be seen as a form of cosmic solace. The suffering and apparent randomness of existence might be part of a designed narrative with a purpose beyond our comprehension. Ultimately, the simulation hypothesis resides in a strange limbo between science and metaphysics. It is notoriously difficult, if not impossible, to falsify with our current understanding. Any evidence we might uncover could itself be part of the simulation, but its power lies in its ability to reframe our most fundamental questions. It forces us to consider that the ultimate limit we face may not be an edge in space or time, but a boundary of information. The cosmos we are trying to understand might not be the deepest layer of reality, but merely the user interface for a reality we cannot directly access, setting a final metaphysical horizon on human knowledge itself. All of these grand cosmic boundaries, the limits of our vision, the nature of reality, even the possibility of a simulation share a common thread. They are questions we are asking. They represent the outermost frontiers of human curiosity, but this very act of asking leads to another, deeply unsettling limit, one that concerns not just empty space or physics, but the potential for other minds out there. We look at the sheer scale of the universe with its hundreds of billions of galaxies, each containing hundreds of billions of stars, and the numbers seem to shout that we cannot possibly be alone. And yet, when we listen, the cosmos is silent. This profound contradiction is known as the Fermi paradox, and it poses what might be the most poignant limit of all, a limit on our knowledge of cosmic companionship. The paradox gets its name from a casual lunchtime conversation in the 1950s. Physicist Enrico Fermi, while discussing the high probability of extraterrestrial life, famously asked, "But where is everybody?" His point was devastatingly simple. The universe is ancient. Our own galaxy, the Milky Way, is over 13 billion years old. Our solar system is a relative newcomer at 4.5 billion years. That means there has been ample time, many billions of years, for other intelligent civilizations to arise, long before we did. Even if interstellar travel is painstakingly slow, a civilization that emerged just a few million years before us could have, in principle, explored or even colonized the entire galaxy by now. A few million years is a mere blink in the cosmic calendar. So, if intelligent life is common, the galaxy should be teeming with activity. We should see evidence of astro-engineering, hear the constant buzz of interstellar communication, or perhaps have already been visited. But we see nothing but silence and emptiness. The sky is not filled with alien megastructures. It is filled with seemingly natural, unaltered stars. This silence is the Fermi paradox, and it suggests there is a powerful, unseen filter that prevents life from progressing to the point where it becomes visible across the cosmos. This leads to one of the most chilling ideas in all of science, the Great Filter hypothesis. The concept is that the evolution of life, from the first self-replicating molecules to a civilization capable of colonizing stars, must pass through a series of critical evolutionary steps. The Great Filter is a barrier along this path that is so difficult to overcome that it effectively stops almost every attempt dead in its tracks. The terrifying question for us is, where is this filter located? Is it in our past, meaning we are an incredibly rare fluke that somehow slipped through? Or is it waiting for us in our future, a challenge that we have yet to face and one that may ultimately spell our doom? If the filter is behind us, we are the lucky ones. This would mean that one of the steps we have already passed is phenomenally improbable. Perhaps the origin of life itself, the transition from non-living chemistry to a primitive, replicating cell, is the Great Filter. Maybe it only happened once in our entire galaxy. Or perhaps the filter is the jump from simple prokaryotic life to complex eukaryotic cells, a transition that took over 1 billion years to occur on Earth. If any of these early hurdles are the showstoppers, then it would explain the silence. The galaxy might be littered with sterile worlds, or planets where life never got past the bacterial stage. In this scenario, we are not just alone in our neighborhood. We might be the only conscious beings in the Milky Way, a solitary spark of intelligence in a vast, silent night. This is a humbling and in some ways a comforting thought, because it means our biggest challenges may still be ahead of us. The far more unsettling possibility is that the Great Filter lies in our future. This suggests that the development of a technological civilization inevitably leads to its own destruction. The steps that seem like milestones of progress, mastery of nuclear energy, genetic engineering, artificial intelligence might actually be suicide pills. It could be that once a species gains the power to alter its world or itself on a planetary scale, it always or almost always uses that power irresponsibly and self-destructs. Another possibility is that the universe is simply a dangerous place, and periodic cataclysms like gamma-ray bursts act as galactic reset buttons, sterilizing vast swaths of space just as civilizations are beginning to emerge. If this is the case, then the silence of the cosmos is a graveyard quiet. It means that the ultimate limit for intelligent life is not the vastness of space, but its own technological adolescence. We look up at the silent stars not as a sign of our rarity, but as an ominous warning of a fate that may await us all. Of course, there are less grim solutions to the Fermi paradox. Perhaps we are looking for the wrong things or in the wrong way. Our searches for extraterrestrial intelligence, known as SETI, have primarily focused on scanning for deliberate radio signals. But a truly advanced civilization might use technologies for communication that are as far beyond radio as the internet is beyond smoke signals, perhaps using neutrinos or gravitational waves, which we are only just beginning to detect. Or maybe intelligent life is common, but it chooses to remain hidden. This is the zoo hypothesis, the idea that Earth is a designated wilderness area, quietly observed by a galactic community that has agreed not to interfere with our development. Another thought is that spacefaring civilizations are simply too alien for us to recognize. Their motivations, their structures, their very existence might be so different from our anthropocentric expectations that we are looking right at the evidence and not seeing it for what it is. They might be silent not because they are dead, but because they are busy with pursuits we cannot even imagine. Ultimately, the Fermi paradox and the Great Filter hypothesis force us to confront the fragility of intelligence. They suggest that the ultimate cosmic limit might not be a wall of fire at the edge of a black hole or a cold, empty future, but a biological or sociological barrier. The universe may be generous with its planets and its chemistry, but incredibly stingy with the gift of lasting consciousness. The profound silence that answers our searches could be the most important message we will ever receive. It is either a testament to our miraculous uniqueness or a solemn warning echoing back at us from a future we have yet to meet. In searching for others, we are ultimately searching for a reflection of our own potential. And the silence holds up a mirror, asking us whether we are capable of navigating the challenges that may have silenced every other voice in the choir of the cosmos. This journey to the edge of the cosmos forces us to confront a possibility even more profound than the limits of space and time. What if the ultimate frontier is not out there among the galaxies, but right here within the confines of our own skulls? We have been exploring horizons built by physics, but perhaps the most significant filter on our understanding of the universe is the very instrument we use to perceive it, the human mind. Our consciousness, that mysterious inner experience of being, and our biological senses act as a profound and inescapable lens, coloring and shaping everything we call reality. The universe we know and describe is not the universe as it truly is in some pure, objective state. It is the universe as it is translated and interpreted by the specific hardware and software of human cognition. Consider for a moment the humble reality of our senses. Our eyes are not all-seeing orbs. They are biological instruments tuned by evolution to perceive only a tiny sliver of the electromagnetic spectrum. We see the world in what we call visible light, but this is just a narrow band of wavelengths nestled between infrared and ultraviolet. A bee perceives a world rich with ultraviolet patterns on flowers that are invisible to us. A pit viper senses the infrared heat signature of its prey in the dark. Their realities, built from their senses, are fundamentally different from our own. We are, in a very literal sense, deaf to the symphony of radio waves that constantly wash over us and blind to the high-energy ballet of gamma rays. Our entire cosmological picture is constructed from the tiny fraction of reality that our instruments, which are ultimately extensions of our senses, can detect and that our brains can process. The majestic spiral of a galaxy is not what we would see if we were there. It is a translation, a representation built from photons that our brains have learned to interpret as color, shape, and depth. This filtering goes far deeper than just our five senses. The very structure of our brain, shaped by millions of years of evolution on the African savanna, is optimized for survival, not for comprehending the true nature of quantum fields or 11-dimensional spacetime. Our cognition is riddled with biases and heuristics that helped our ancestors avoid predators and find food, but which now limit our ability to grasp cosmic truths. We instinctively think in terms of cause and effect, of objects existing in definite locations, of a flowing, universal time. Yet, modern physics consistently tells us that these are approximations, useful illusions that break down at the extremes. The quantum world operates on probability and superposition, where particles don't have a definite location until they are measured. At the event horizon of a black hole, time and space swap roles. These concepts are not just difficult to understand, they are almost impossible to intuitively grasp because our brains did not evolve to navigate such realms. We are like fish trying to understand the concept of fire. Our entire existence is predicated on a medium that makes the phenomenon impossible. The universe might be filled with dimensions and properties that are simply beyond the computational capacity of our neural architecture to model. This leads to a radical question. Is a truly objective view of the cosmos even possible? Or are we forever trapped in a universe of our own subjective making? The color red, for example, has no intrinsic redness. It is a specific wavelength of light that, when it strikes the photoreceptors in our eyes, triggers a cascade of neural events that our brain subjectively experiences as the sensation of red. There is no way to know if your experience of red is the same as mine. We can agree on the wavelength, but the qualitative experience, what it is like to see red, is private. Now scale this up to every facet of reality. The grandeur of a nebula, the concept of vastness, the chill of empty space. These are all interpretations generated by our consciousness. We are not passive observers of a pre-existing reality. We are active participants in its creation. The cosmos as we know it is a collaboration between whatever is out there and the intricate wiring of the human mind. This doesn't mean that reality is an illusion, but rather that our access to it is indirect and heavily processed. It suggests that the ultimate cosmic limit may be a biological and psychological one. The mysteries of dark energy and the multiverse might not just be puzzles waiting for a bigger telescope or a more powerful equation. They might be concepts that lie outside the natural categories of human thought. Perhaps other intelligences in the universe with different evolutionary paths and sensory apparatuses would construct entirely different cosmologies, not because they are wrong, but because their reality is filtered through a different lens. Our search for the ultimate limit, then, becomes a deeply introspective one. To understand the cosmos, we must first understand the instrument through which we perceive it. The final frontier may not be at the edge of the observable universe, but in the unexplored territory of our own consciousness, the very source of all the questions we have been asking. Throughout our journey to the edge of knowledge, we have repeatedly encountered a fracture, a deep crack in the foundation of physics that appears whenever we push our understanding to the absolute extreme. At the heart of a black hole singularity, and at the moment of the Big Bang itself, our two most powerful and successful theories of reality simply break down and refuse to speak to one another. On one hand, we have general relativity, Einstein's magnificent description of the cosmos on its largest scales. It paints a picture of a dynamic, flexible spacetime, where gravity is not a force but the curvature of this fabric by mass and energy. It perfectly predicts the orbits of planets, the bending of light, and the expansion of the entire universe. On the other hand, we have quantum mechanics, the astonishingly accurate rulebook for the subatomic world. It describes a realm of probability and uncertainty, where particles can be in multiple places at once and where empty space fizzes with fleeting quantum activity. Both theories have been tested to incredible precision, and both are unequivocally correct within their own domains. The problem is that these domains are not separate. They collide in the most violent and dense environments imaginable, and when they do, they produce nonsensical answers. The greatest unsolved problem in physics is to weave these two disparate descriptions into a single, coherent tapestry, a theory of quantum gravity. The core of the conflict is a clash of fundamental principles. General relativity is a classical theory. It is deterministic and smooth. It tells us that if you know the state of a system at one moment, you can perfectly calculate its state at any future moment. Space-time is a continuous, unbroken fabric. Quantum mechanics, however, is inherently probabilistic and granular. It insists that at the tiniest scales, the world is fuzzy, and properties like position and energy are not definite until they are measured. This creates an irreconcilable tension when you try to apply both sets of rules to the same event. Consider what happens when you try to describe the center of a black hole. General relativity's equations predict an infinitely dense, infinitely small point, a singularity where space-time curvature becomes infinite. But physicists abhor infinities. They are almost always a sign that a theory has been pushed beyond its limits. A singularity is a place where the smooth, geometric picture of general relativity is expected to be replaced by a quantum description. But when we try to apply quantum rules to this point of infinite density, the mathematics explodes into nonsense. We simply do not have the tools to describe it. This dilemma is not confined to black holes. It strikes at the very origin of everything, the Big Bang. If we run the cosmic film backward, general relativity takes us all the way back to a state where the entire universe was compressed into a single point of infinite temperature and density, another singularity. This is the ultimate temporal barrier to our knowledge. To understand what happened at time zero, or even what caused the Big Bang, we need a theory that can handle these extreme conditions. We need a framework where the classical smoothness of spacetime can transition into or emerge from a quantum description. Without quantum gravity, the question, what came before the Big Bang, might not even be a valid question, as time itself may have emerged from a quantum state we cannot yet describe. A theory of quantum gravity would be the ultimate key, allowing us to peer past this initial horizon and understand the true birth of space and time. The quest for this unified theory has given rise to several brilliant yet unproven candidates. Perhaps the most well-known is string theory. It proposes a breathtakingly elegant solution. The fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. Just as different vibrations of a violin string produce different musical notes, the different resonant frequencies of these fundamental strings would give rise to all the diverse particles we see, from electrons to photons. In this framework, gravity emerges naturally from a specific pattern of vibration, corresponding to a particle called the graviton. Crucially, string theory requires the existence of extra dimensions of space curled up into sizes near the Planck length to make its mathematical consistency work. While it elegantly unites gravity with the other forces, string theory has been criticized for its current inability to make testable predictions that could confirm or refute it. Another compelling approach is loop quantum gravity. Instead of proposing new fundamental objects, it takes a more direct path by rewriting the equations of general relativity in a language compatible with quantum principles. It suggests that space-time itself is not continuous, but is composed of a fabric of tiny, finite loops woven into a network. Think of it as the cosmic equivalent of a piece of cloth. From a distance, it looks smooth and continuous, but up close, you see it is made of individual, interwoven threads. In loop quantum gravity, there is a smallest possible unit of space and time, a quantum of volume which prevents the formation of true singularities. This leads to a fascinating alternative to the Big Bang, a big bounce where our universe was born from the collapse of a previous cosmic cycle. These theories, and others like them, represent humanity's most ambitious intellectual endeavors, attempts to solve a puzzle that lies at the very boundary of what is knowable. Discovering the correct theory of quantum gravity would do more than just solve mathematical inconsistencies. It would revolutionize our understanding of reality. It would finally allow us to understand the true nature of a black hole's interior and resolve the black hole information paradox. It would reveal the microstructure of space-time, answering whether it is indeed granular or foamy at the Planck scale. Most profoundly, it would complete our picture of the universe's history, taking us from the pure quantum realm of the Big Bang to the classical, expanding cosmos we inhabit today. The search for this theory is the final, and perhaps most important, step in our journey to comprehend the ultimate cosmic limits. It is the quest for a single, unified language to describe everything from the dance of galaxies to the flutter of a quantum field, a theory that would truly tell us what the universe is made of at its deepest level. We have traveled an astonishing path together, from the grand, star-filled expanse of our observable universe all the way down to the ghostly grain of space-time at the Planck scale. We have peered over the cosmic horizon where galaxies vanish into the expanding dark and contemplated the fiery walls of a black hole's event horizon. We have journeyed forward in time to witness the cold, silent conclusion of the heat death and envisioned the violent alternative of a big rip. We have even dared to consider realities beyond our own in a multiverse of infinite possibilities and question the very nature of our existence within a simulated reality. At every turn, we have encountered not a single, simple boundary, but a series of profound and layered frontiers, each defined by the fundamental laws of physics and the limits of our own perception. The ultimate cosmic limit is not one thing, it is a conversation between what is out there and what we are capable of knowing. This journey reveals something extraordinary about our place in the cosmos. We are beings of a middle world, exquisitely adapted to the scales of life on Earth, yet gifted with a curiosity that propels us to ask questions about the unimaginably vast and the infinitesimally small. It is a testament to human ingenuity that we can even conceive of these limits, using mathematics and imagination to map the edges of reality itself. The quest to understand these boundaries is more than a scientific endeavor, it is a deeply human one. It speaks to our innate desire to explore, to understand our origins, and to grapple with our ultimate destiny. Whether it is the sheer scale of the universe that humbles us, or the bizarre rules of the quantum world that confound us, each frontier reminds us that the cosmos is far stranger and more wonderful than we could ever have imagined. And so, we end this exploration not with a definitive answer, but with an invitation to reflect. Every limit we've discussed represents a different kind of challenge, a barrier of distance, a wall of time, a cliff edge of knowledge, or a mirror reflecting the limits of our own mind. Some are haunting in their finality, like the event horizon of a black hole. Others are deeply unsettling in their implication, like the great filter of the Fermi paradox. Some fill us with awe at the sheer grandeur of existence, like the infinite expanse suggested by a flat universe. Each of these frontiers touches a different chord within us. So now we turn the question over to you. As you look out at the night sky or simply ponder the nature of reality, which of these ultimate cosmic limits fascinates you the most? Is it the idea that we may be living in just one bubble in an infinite multiverse? or the chilling possibility that the universe is accelerating toward a cold and lonely end? What concept sends a shiver down your spine or sparks your imagination? Share your thoughts in the comments below. We would love to hear which frontier captures your curiosity. And if you enjoyed this journey to the edge of understanding, be sure to subscribe for more adventures into the deepest mysteries.